Hi, my name is Minho Kwon, and this is homework 2, set 6. Today, I'll review shrinkage methods within Lasso and apply them to the college dataset to predict the number of applications. I'll compare linear regression to Rich and Lasso, walk through tenfold cross-validation, and finish with discussions. Before I get into Rich and Lasso, I'll briefly see where the shrinkage methods fit in model selection. Unlike discrete stepwise methods, Rich and Lasso continuously shrinks coefficients by adding a penalty term, improving stability and reducing variance. This penalty discourages large coefficients, reducing variance and improving generalizations, even if it introduces a bit of bias. Mathematically, it's just a least square plus a penalty term on the betas. In the next slide, I'll compare Rich and Lasso and see how their penalties differ from geometrically and practically. This is Rich regression, which is called L2 regularization. Rich adds a penalty term, the sum of square coefficients, to the usual least square loss. We minimize RSS plus lambda times the sum of beta j squared, where lambda controls the penalty strength. When lambda equals 0, Rich is identical to OLS, the ordinary least squares. As lambda increases, all coefficients are smoothly shrunk towards 0, but never exactly 0. This shrinkage makes the model less sensitive to noise in the training data, reducing variance and preventing overfitting. That's the bias-variance trade-off. Also, since the L2 penalty is differentiable, which has a simple closed form solution, making it efficient to compute. Here, multicollinearity means predictors are highly correlated. When predictors are correlated, OLS coefficients become unstable. Even small data changes can flip their signs. As a result, OLS shows high variance and poor generalization. Mathematically, OLS here, under collinearity, some eigenvalues of xtx are near 0, so the inverse of xtx blows up and producing huge noisy beta estimates. Which fixes this by adding a small constant lambda to the diagonal. This stabilizes the inversion, so every eigenvalue increases by lambda, keeping the matrix invertible and reducing beta's variance. We do add slight bias, but the overall MSE drops, a direct result of the bias variance trade-off. The equation below shows this clearly. The usual RSS term plus lambda times the sum of squared coefficients separating the residual and penalty parts. This is Lasso regression, which is called L1 regularizations. Lasso adds a penalty equal to the sum of the absolute values of the coefficients to the least square loss. The tuning parameter lambda controls the penalty strength. When lambda is small, it behaves like OLS. As lambda increases, coefficients are shrunk more strongly towards 0. The key feature of Lasso is that for large lambda, some coefficients become exactly 0, meaning those predictors are automatically removed from the model. So Lasso performs both shrinkage and variable selections, producing a sparse interpretable model. Unlike Rich model, the L1 penalty is not differentiable at 0, so it has no closed form solution and must be solved numerically. Now I'll see when two predictors are almost identical, Lasso tends to keep one and drop the other one randomly, causing unstable variance selection. As an alternative, ElasticNet solves this by combining Rich and Lasso's penalty, like this one. ElasticNet combines L1 and L2 penalties to gain both sparsity and stability. This one shows the geometric difference between Rich and Lasso. Both minimize the RSS, but under different constraints. Left one is diamond-shaped region, Lasso. Right side Rich is circular one. The red ellipses represent RSS contours with the OLS solution beta hat at the center. The optimal Rich or Lasso estimates is where the smallest ellipse first touches the constraints boundary. You may wonder why RSS forms ellipses. It's because RSS is a quadratic function. When predictors are correlated, xtx is stretched in one direction, so the ellipse becomes elongated. With Uncorrelated predictors is nearly circular form. On the right side, ridge regression's constraint is smooth and circular, so the RSS ellipse usually touches the boundary at non-axis point. As a result, all coefficients are continuously shrunk towards zero, but none of them become exactly zero. This is called continuous shrinkage. On the left, Lasso regression has a diamond-shaped constraint with sharp corners along the axis. Because of those corners, the RSS ellipse often touches the boundary at a corner, forcing one or more coefficients to be exactly zero. That's why Lasso performs variable selection, where Rich only shrinks coefficients without eliminating predictors. You can think of why this as soft-stress folding is small coefficients drop to zero, while larger ones are reduced but remain non-zero. This remains the cross-validation used to find lambda. It can be divided into LLO-CV and K4-CV methods. In today's problems, we use the 10-4-CV method for computational efficiency and variance stability. Let's check the slides for detailed explanations for each method. Now I'll see our dataset. We are using the college dataset, which contains various statistics on 777 US universities and 18 variables. The column private indicates whether the institution is private or public. This is our only qualitative predictor. The response variable we want to predict is apps, which represent the number of applications received by each university. All code was written in Python on Google Colab. I first insert and import the necessary libraries and load data, and also convert the private column from yes, no to 1 or 0 so it can be used in Rich and Lasso, and then check the first few rows and dataset shape. Before training data, I split the dataset into training and test sets. I use 70 and 30 split, giving 547 observations for training and 234 for testing. The larger portion of 70% allows the model to learn the data patterns, while the 30% test set provides a fair evaluation of generalization performance. We also fixed random state equal 1 to ensure the same data shuffle each time, which makes our results reproducible. And this is code. And now I first fit a baseline linear regression model using the training data. I use the least squared method to estimate the coefficients beta that best fit the training data. Then I use this model to predict apps in the test set and calculated the test error using the mean squared error MSE, comparing the predicted values with the actual number of applications. This gives us a baseline performance to compare later with Rich and Lasso. Here, I first fit linear regression model using scikit-learn. We first fit separate predictors X and the response variable Y apps for both training and test sets. Then, I train the model using linear regression and make predictions on the test data. On the right, you can see the estimated coefficients. And here, I calculated the test MSE for linear model. Now I build the rich regression model using the rich CV function from scikit-learn, which automatically performs cross-validation to find the optimal lambda value. First, I generate 100 lambda candidates on logarithmic scale, ranging from 0.01 to 10,000. This wide range ensures that both weak and strong regularization levels are tested. Next, I learn 10-4-CV within the training set to compute the MSE for each lambda. The lambda with the lowest average MSE is chosen as the optimal parameter. Then I refit Rich on the full training set using this lambda, and finally evaluate it on the test set using the MSE. This is the diagram of cross-validation used in Rich and Lasso regression. Here you can see the cross-validation results for Rich regression. The x-axis shows lambda, the regularization strength on a log scale, and the y-axis shows the MSE from cross-validation. When lambda is very small, the model has high variance leading to slightly larger MSE. When lambda becomes too large, bias dominates and the MSE rises sharply. Around lambda is 0.01, the CV MSE reaches its minimum. This point gives the most stable balance between bias and variance. The resulting test MSE is about 642,765, which is nearly the same as the linear model's MSE. This happens because lambda is very small, so rich behaves almost like the linear model with minimal regularization. Here we see rich model implementation with CV. The key steps are standardization and using pipeline. First, standardization ensures all predictors are on the same scale. Without it, large-scale variables would get an excessive penalty, while small-scale ones would receive almost none, leading to unfair regularization across variables. Second, the pipeline integrates scaling and reach together. It standardizes the training data inside each CV fold, then fits and validates the model. This avoids data leakage because no information from the test fold is used during training. In short, combining standardization and pipeline gives fair, reliable CV results for reach. Now we see the cross-validation results for Lasso regression. The x-axis shows the lambda on a log scale and y-axis shows the CV mean squared error. For small lambda values, the model tends to overfit, giving high variance. For large lambda, coefficients are overly penalized, increasing bias and MSE again. Around lambda is 21.5, the MSE reaches its minimum, representing the optimal bias variance trade-off. This lambda is much larger than richest lambda, which means Lasso applies strong regularizations, shrinking more coefficients exactly to zero and producing a sparser model. In short, as lambda increases, the model becomes simpler and more interpretable, but at the cost of slightly higher bias. The Lasso model shows a higher test MSE, about 689,460, while rich and linear around 642,000. This happens mainly because Lasso can oversimplify the model. By setting some coefficients to zero, it may remove variables that still carry useful information, causing a small information loss and slightly higher prediction error. Under multicollinearity, Lasso also tends to keep only one of several correlated predictors, and this arbitrary selection can make the model less stable. In our dataset, most predictors seem to contain meaningful signals, so removing some of them actually increased bias more than reduced variance. Therefore, rich performs slightly better because it shrinks rather than eliminates coefficients. Here we examine the non-zero coefficients selected by Lasso model. Out of 17 predictors, 14 remain non-zero, while 3 variables, which is F term, undergrad, books, and personal, were set exactly to 0. This means Lasso automatically removed predictors that had the least influence on predicting apps. Looking at the correlation heat map on the right side, we can see the F undergrad is highly correlated with accept and enroll, indicating multicollinearity. So Lasso likely dropped it because its information was already captured by those variables. Meanwhile, books and personal shows weak correlations with apps, so they had minimal predictive power and were also excluded. So Lasso simplified the model by removing redundant and low-impact predictors, resulting in a more interpretable, sparse model. The process starts on the left with lambda tuning. We generate 100 lambda values on a log scale and run 10 for CV for each one. Inside the pipeline, the data are first standardized using standard scalar, and then the Lasso model is trained. This ensures consistent scaling across folds and prevents leakage. For each lambda, we compute the CV, MSE, and select the lambda with the lowest average error as optimal. Next, in the center block, we retain the final Lasso model on the full training data using this optimal lambda and evaluate its performance on the test set using MSE. After that, we extract the non-zero coefficients, identifying which predictors were kept by the model. Finally, the right block builds a correlation heat map to visualize how the selected predictors related to each other. And now, first, when comparing the test MSE, the difference among the three models, linear, rich, and lasso, are minimal. Since our dataset has far more samples than predictors, the risk of overfitting is low. Rich and Lasso slightly reduce variance by adding bias, but in this case, bias increases outweighed by benefit, so their performance is almost identical to the linear model. The RMSE for the linear model is about 801 applications. I think it is reasonably good accuracy considering that the average number of applications is around 2,200 and the maximum exceeds 48,000. And second, looking at dataset characteristics, the college data shows no severe multicollinearity with most correlations below 0.7. Therefore, the linear model remains stable and the extra regularization from Rich or Lasso offers only limited improvement. In short, when the dataset are well behaved and overfitting is mild, the simpler linear model can perform just as well. Here, I changed the training test split to see how training data size affects regularization and model performance. Surprisingly, all three models shows lower test MSE with the smaller training set. When training data increases, the risk of overfitting increases, so cross-validation automatically chooses a larger lambda, applying stronger regularization. As you can see, Lasso's lambda increases from 21.5 to 38.7, and the number of non-zero coefficients drop from 14 to 10, simplifying the multiple, which remains stable at lambda is 0.01, showing its robustness to data size. Overall, the test performance improved because stronger regularization reduced model variance and overfitting, leading to more generalization. In this case, I reduced the total sample size from 777 to 100 to see how each model behaves with less data. As we can see, both linear and rich regression shows much higher test MSE. Their variance increases due to small training set. However, Lasso adapts automatically by selecting a much larger lambda and shrinking most coefficients to zero. Only 6 predictors remain non-zero. These stronger regularization helps Lasso avoid overfitting, achieving a much lower test MSE even with fewer data points. This result highlights Lasso's strengths in small sample, high variance settings, where it can stabilize models and maintain good predictive performance. Finally, let's look at real-world applications of Rich and Lasso in research. First case is Lasso regression is often used to improve accuracy and reduce overfitting the air pollution prediction area. Environmental data usually contain many correlated variables, such as pollutants and weather factors. Lasso helps by performing feature selection, automatically identifying the most important predictors. As a result, it reduces noise and improves both model interpretability and prediction stability compared to ordinary linear regression. Second, in genetic data analysis, rich regression is applied to large-scale gene expression studies where the number of variables greatly exceeds the number of samples, so P is much larger than N. Rich handles strong multicollinearity and outliers effectively, providing robust, stable, and efficient prediction results. Overall, Lasso is preferred when feature selections and interpretability are key, while Rich is stronger for stability in high-dimensional or noisy data. So this is end for Set6, and thank you for watching this video.